In 1838, a German astronomer named Friedrich Bessel accomplished something that humans had been attempting for over 2,000 years, using a technique called stellar parallax, measuring the tiny shift in a star's apparent position as Earth orbits the Sun. The vessel calculated the distance to a star called 61 Cygni. The number he got was almost incomprehensible, about 10.3 light years or roughly 60 trillion miles. When Bessel announced his result, it caused a kind of existential shock in the scientific community. Astronomers had suspected that stars were far away, but this far, 60 trillion miles to one of the nearest stars, the universe had suddenly become vastly larger than anyone had truly grasped. And 61 Cygni isn't even particularly distant. It's one of the closest stars to our Sun. The galaxy contains hundreds of billions of stars, most of them incomparably farther away. I want to take you on a journey today, not a journey through space that, as we'll see, is the problem. I want to take you on a journey of understanding. I want you to truly grasp, not just intellectually, but viscerally, why no species, not humans, not aliens, not any form of intelligent life that could ever evolve anywhere in the universe, can cross the galaxy. This isn't a statement about current technology. It's not about what we can or can't build today. It's a statement about the fundamental nature of space, time, and physical law. The galaxy is a prison, and the prison walls aren't made of matter. They're made of distance itself. Let me start with some numbers. And I apologize in advance because these numbers are going to be hard to absorb. They're going to slide off your brain like water off glass because human minds simply aren't equipped to comprehend scales this large. But I'm going to try anyway. The Milky Way galaxy is approximately 100,000 light years in diameter. A light year is the distance that light travels in 1 year. Light is the fastest thing in the universe. Nothing can exceed it. Nothing can even match it if it has mass. Light travels at 186,282 m per second, not per hour, per second. In 1 second, light could circle the Earth 7 and 12 times. In 1 year, traveling at that incomprehensible speed, light covers about 5.88 trillion miles. That's 5,880 billion miles. Almost 6 trillion miles traveled in a single year. The galaxy is 100,000 of those. Let me try to make this concrete. In 1977, NASA launched 2 spacecraft called Voyager 1 and Voyager 2 on missions to explore the outer planets. After completing their planetary tours, both spacecraft kept going, heading out into interstellar space. They're still going today, still sending back data, still functioning after nearly 50 years of continuous operation. Voyager 1 is now the most distant human-made object in existence. It has traveled approximately 15 billion miles from Earth. It's moving at about 38,000 miles per hour, faster than any bullet, faster than any airplane. One of the fastest sustained velocities any human spacecraft has ever achieved. And after 50 years of travel, after covering 15 billion miles, Voyager 1 has completed less than 1/5% of 1% of the distance to the nearest star. Let me say that again because it's important. 50 years, 15 billion miles, less than 0.2% of the way to Proxima Centauri, which is only 4.24 light years away. If Voyager 1 were heading toward Proxima Centauri, which it isn't, it would be heading in a different direction. It would arrive in approximately 73,000 years. That's longer than modern humans have had language. That's longer than any civilization's ever lasted. And that's just to reach the nearest star. Now consider the galaxy. At Voyager 1's speed of 38,000 miles per hour, crossing the Milky Way from one side to the other would take approximately 1.7 billion years. I want you to sit with that number for a moment. 1.7 billion years. When you started your journey, Earth was a different world. Complex multicellular life would barely have begun to emerge. The continents would be arranged in unfamiliar configurations. The atmosphere would have a different composition. There would be no plants on land, no animals, no forests, no grasslands, just rock and water and microbes. By the time you arrived at the other side of the galaxy, 1.7 billion years later, you wouldn't recognize home. Even if you could somehow return, the sun would be significantly brighter, perhaps bright enough to have boiled away Earth's oceans. Whatever descendants of humanity might still exist, if any, would be as different from us as we are from ancient single-celled organisms. They wouldn't be human in any meaningful sense. They might not even be recognizable as life to our eyes. And this assumes you could survive the journey. You couldn't. Nothing could. No spacecraft humanity has ever built could survive for 7 billion years. Voyager 1, our most distant emissary, will be dead within a decade or two. Its plutonium power source is decaying, producing less electricity each year. Soon, it won't have enough power to run its instruments or transmitters. It will become a silent, dead hulk, drifting through interstellar space forever. Even if we built a spacecraft designed for extreme longevity, it couldn't last millions of years, let alone billions. Materials fatigue over time. Metal crystals slowly deform under stress. Radiation from cosmic rays damages electronic circuits. Micrometeorites, tiny grains of dust moving at tremendous speeds, sandblast any surface they encounter. Seals degrade. Lubricants evaporate. Moving parts wear out. The cold of interstellar space, just a few degrees above absolute zero, makes materials brittle. The heat from passing stars could warp structures. The vibrations from onboard systems accumulated over millions of years could shake a spacecraft apart. Nothing lasts forever. Nothing lasts for a billion years. Nothing could survive the journey across the galaxy at Voyager speeds. But surely, you might think, we could go faster. Voyager's primitive technology, nearly 50 years old, surely a more advanced civilization could build faster spacecraft. Yes, they could. Let's explore what that would mean. Imagine a spacecraft capable of traveling at 10% of the speed of light. This is roughly 67 million mph, about 1,760 times faster than Voyager 1. This is far beyond anything humanity can currently build, but it's not physically impossible. Various proposals for interstellar travel, nuclear pulse propulsion, fusion rockets, antimatter engines, laser push sails might theoretically achieve velocities in this range at 10% of light speed. Crossing the galaxy would take 1 million years. 1 million years is still an almost incomprehensible span of time. Modern humans, Homo sapiens, have existed for about 300,000 years. Our entire species, from the first anatomically modern humans in Africa to you reading this today, fits within 1/3 of the time needed for a galactic crossing at 10% of light speed. Human civilization, cities, agriculture, writing, technology has existed for about 10,000 years. The entire history of everything we consider civilization, from the first Sumerian cities to smartphones and space stations, represents one of the journey time. What language would your crew speak after 1 million years? What culture would they maintain? What connection would they have to whoever launched them? After 1 million years, the descendants of your original crew wouldn't be the same species. Evolution would have reshaped them, adapted them to their spacecraft environment, made them into something no longer human. Let's go faster still. Imagine we could achieve 50% of light speed, half the maximum velocity the universe allows. This would require energy production beyond anything humanity has ever contemplated. But let's grant it as a thought experiment. At 50% of light speed, the galaxy crossing takes 200,000 years. This is still longer than Homo sapiens has existed, still longer than any technologue. Why has been maintained, any culture has been preserved, any species has remained unchanged. 200,000 years ago, our ancestors were making simple stone tools in Africa. They had no idea it would become the science of astrometry. He never imagined spacecraft or interstellar travel. The very concept would have seemed like fantasy. But he knew, perhaps better than anyone alive at the time, just how far the stars truly were. He had measured the abyss and found it vast beyond comprehension. The galaxy is 100,000 light-years across. And that number isn't just large, it's impossible. In 1993, the Hubble Space Telescope pointed at a tiny, seemingly empty patch of sky near the Big Dipper constellation. The patch was so small that it could be covered by a grain of sand held at arm's length. To the naked eye, and even to ground-based telescopes, this patch appeared completely black, a void in the heavens where nothing existed. Astronomers decided to take a risk. They pointed Hubble at this apparent emptiness and let it stare for 10 consecutive days, gathering light from the darkest corner of the cosmos they could find. Many thought it was a waste of valuable telescope time. What could possibly be there? What they found changed our understanding of the universe forever. The resulting image, called the Hubble Deep Field, revealed approximately 3,000 galaxies in that minuscule patch of darkness. Not stars, galaxies, each one containing hundreds of billions of stars, each one representing an island universe unto itself, each one impossibly, incomprehensibly far away. The deep field image is one of the most beautiful photographs ever taken. It's also one of the most terrifying. It shows us what lies beyond our local cosmic neighborhood, a vastness so immense that it defies human comprehension. And between those galaxies, between those stars, lies something that looks like nothing, but is actually something that would kill any traveler foolish enough to venture into it. The space between stars is not empty. And understanding what fills that space is essential to understanding why crossing the galaxy is impossible. Let me take you on a journey through the interstellar medium, the substance that fills the 100,000 light-years between one side of our galaxy and the other. Even if you could somehow solve the problem of distance, even if you could travel fast enough to make the journey in a reasonable time, the environment itself would destroy you long before you arrived. Start with the most obvious challenge. The cold interstellar space has a temperature of approximately 2.7 Kelvin. That's 2.7 above absolute zero, the coldest possible temperature where all molecular motion ceases. This temperature comes from the cosmic microwave background radiation, the faint afterglow of the Big Bang itself, which permeates all of space with a whisper of ancient heat. 2.7 Kelvin is cold, beyond anything in human experience. At this temperature, nitrogen freezes solid. Oxygen becomes a pale blue crystal. Carbon dioxide is hard as rock. Even hydrogen, the lightest element, hovers just above its freezing point. You might think this cold is manageable. After all, we've sent spacecraft to the outer solar system where temperatures drop to dozens of degrees above absolute zero. The Voyager probes have survived in deep space for nearly 50 years. Surely we could engineer something to handle interstellar cold. But there's a crucial difference. Spacecraft in our solar system, no matter how distant, still receive some warmth from the sun. They're still bathed in solar radiation, however faint. They're still within the heliosphere, the bubble of solar wind that extends to the edges of our solar system. They have a reference point, a source of energy, a connection to home in interstellar space. There is nothing, no sun, no warmth, no external energy source whatsoever. Just the cosmic microwave background, a uniform bath of radiation so faint that it barely registers on our most sensitive instruments. A spacecraft crossing the galaxy would need to generate its own heat for millions of years. Think about what that means. Every heating system we know. How to build requires energy. Nuclear reactors need fuel. Radioisotope generators decay over time. Chemical reactions consume reactants. All of these have finite lifespans measured in years or at most decades. Plutonium-238, the most common radioisotope used in spacecraft power systems, has a half-life of 87. 7 years, after a century, half its power is gone. After 2 centuries, 3/4 is gone. After 1,000 years, less than 1% of the minimum journey time to cross the galaxy, your plutonium power source would be essentially dead, generating less than a trillionth of its original output. Nuclear fish reactors could theoretically last longer, but they too have limits. Fuel eventually runs out, reactor components degrade under neutron bombardment. Control systems fail. No nuclear reactor has ever operated for more than a few decades. And we're talking about timescales of millions of years. Without heat, everything fails. Electronics stop working as circuits become superconducting or simply crack from thermal stress. Lubricants freeze solid, seizing every mechanical system. Seals become brittle and shatter, venting precious atmosphere into the void. The structural materials of the spacecraft itself become so fragile that the slightest vibration could cause catastrophic failure. The cold alone would kill any spacecraft within millennia, and millennia are nothing compared to the journey times required. But the cold, as lethal as it is, isn't even the primary threat. Now consider radiation. Space is permeated with high-energy particles called cosmic rays. Despite their name, cosmic rays aren't rays at all. They're particles, primarily protons, and heavier atomic nuclei accelerated to tremendous energies by the most violent events in the universe. Supernova explosions, neutron star collisions, the accretion disks around black holes. These cosmic accelerators launch particles outward at nearly the speed of light, and those particles fill the galaxy in every direction. On Earth, we rarely think about cosmic rays because we're protected by multiple layers of shielding. Our planet's magnetic field deflects many charged particles before they can reach the surface. Our thick atmosphere absorbs most of what gets through, converting high-energy particles into harmless cascades of secondary particles that dissipate before reaching the ground. In space, these protections don't exist. In low Earth orbit, spacecraft still receive partial protection from Earth's magnetic field. In interplanetary space, the sun's magnetic field extends outward, creating a heliosphere that deflects some galactic cosmic rays. The radiation environment is dangerous but manageable, but in interstellar space, outside the heliosphere, there is no magnetic shielding whatsoever. Your spacecraft is exposed to the full intensity of galactic cosmic radiation particles that have been accumulating and accelerating throughout the galaxy's history. particles with energies millions of times higher than anything we can produce in our most powerful particle accelerators. A single cosmic ray proton with enough energy can pass completely through a spacecraft, leaving a trail of ionization in its wake. It can flip bits in computer memory, causing software errors. It can damage DNA in living cells, causing cancer and genetic mutations. It can knock atoms out of crystal lattices and metals, weakening structural materials. Over short periods, these effects are minor inconveniences. We design spacecraft electronics to tolerate occasional bit flips. We accept increased cancer risk for astronauts on long missions. We use materials that can handle some radiation damage without failing. But over the time scales required to cross the galaxy, the cumulative damage becomes catastrophic. Studies of radiation effects on spacecraft materials suggest that even heavily shielded structures would accumulate fatal levels of damage within approximately 50,000 to 100,000 years. The crystal struct. Euros of metals would be so disrupted by accumulated radiation damage that they'd lose their strength. Polymers would be broken down into useless fragments. Electronic components would fail completely as their semiconductor junctions were destroyed by accumulated particle strikes. 100,000 years sounds like a long time. It's not. It's less than 1/10 of the time needed to cross the galaxy at Voyager speeds. Even at 10% of light speed, 100,000 years represents only 10% of the journey time. Long before you reach the other side of the galaxy, your spacecraft would be a radiation-damaged hulk. Its structure weakened to the point of failure, its electronics long dead, its crew, if it carried any, killed by accumulated radiation exposure. And this is just from the steady background of cosmic rays. There are far more dramatic radiation events to worry about. Supernova, the explosive deaths of massive stars, release more energy in a few seconds than the sun will produce in its entire 10 billion year lifetime. Much of this energy takes the form of radiation, gamma rays, X-rays, ultraviolet light, and a flood of high-energy particles that rush outward at nearly the speed of light. If your spacecraft happened to be within a few dozen light-years of a supernova when it exploded, the radiation pulse would be instantly lethal. Your crew would die within seconds, their bodies flooded with enough radiation to destroy every cell. Your electronics would be fried by the electromagnetic pulse. Your spacecraft's surface would be heated to incandescence, possibly vaporizing entirely. Supernova are relatively rare events, only 1 or 2 per century in our galaxy. But over the time scales of a galactic crossing, you'd experience many of them. A journey taking 1,000,000 years would see 10,000 supernova explode somewhere in the galaxy, even if most were too far away to be immediately dangerous. Statistically, some would occur close enough to damage or destroy your spacecraft. You might try to plot a course that avoids regions where supernova are likely steering clear of massive young stars that could explode soon, but stars don't announce their intentions. A star that appears stable today might explode tomorrow, or in 1,000 years, or in 10 million years.